Forces, there are only a few truly fundamental ones. There's the gravitational force, the electric force and the magnetic force that we usually put together and call the electromagnetic force, the strong nuclear force, and the electroweak force, which I won't talk about because it's not in the IB program. So let's start talking about the gravitational force, which is the force of attraction between any two masses in the universe. And this force is equal to the product of the two masses divided by the square of this distance separating them times this g, which is the gravitational constant, equal to 6.67 times 10 to the minus 11. How do we know the units of g? Well, on this equation, let's multiply by r squared and divide by m1, m2 on both sides. We obtain something in newtons times meter squared divided by kilogram squared, so per kilogram squared. In a previous video, we studied the gravitational force between the Earth and the Moon. Let's call it F Earth Moon, FEM. And we found that the magnitude of that force was approximately equal to 2 times 10 to the 20 newtons, so quite a big number here. Now, what about an apple that's hanging from a tree? What's the gravitational force attracting the apple and the Earth? Let's call it FA, like force on apple. Okay, so the gravitational force on the apple, the magnitude of that, if we apply the law that we see up there, the gravitational law, we find that it's equal to what? To g times the mass of the Earth, okay, I'm noting large M, the mass of the Earth, times the mass of the apple, okay, I'm noting with a little red M the mass of this apple, divided by the radius of the Earth, because this is the distance separating the apple from the center of the Earth, and taking the square of that. So actually there's an easier way to do this because we use that number so much, everything I wrote in green here, which is the constant g, this 6.67 times 10 to the minus 11, times m, the mass of Earth, divided by the square of the radius. This, we actually simply have a constant that we use often for this, which is small g, which is 9.8 newtons per kilogram. And this force on the apple, the gravitational force on the apple, we also call it weight. So let's just rename it weight of the apple. And the weight of the apple is therefore equal to what? To m, the mass of the apple, times everything I wrote in green here, gm over r squared, which is equal to this small g, which is the strength of the gravitational field on the surface of the Earth. Okay, so let's assume that an apple usually weighs 100 grams. So we have 0.1 kilograms times approximately 10 newtons per kilogram, which gives us a force of 1 newton. So now you can compare the force on the moon and the force on the apple. There's 20 orders of magnitude of difference. Now let's take a look at the hydrogen atom, which has an electron and a proton. What do you think is the gravitational force between the proton and the electron? Pause this video and try to find the answer on your own on Googling the data that you need. Okay, so here's the answer. What we need first is the mass of the electron and the mass of the proton, as well as the distance that separates them. And here's the data I found from Google. Mass of the electron, distance between the electron and the proton, and mass of the proton. Okay, then we simply plug in this data in the formula. We have the gravitational force between the proton and the electron equal to the gravitational constant times the product of the masses divided by the square of the distance between the proton and the electron. And when we plug this in our calculator, we find a force of approximately 3.7 times 10 to the minus 47 newtons. And this is a tiny force. You'll actually realize when we'll talk about the electric force next that this is negligible compared to the electric force of attraction between the electron and the proton. Okay, let's move on now to the electric force, which is a force of attraction or repulsion between two charges. Okay, so the fact that it's attractive or repulsive depends on the sign of the charges. If we have like charges, so plus plus or minus minus, we have a repulsive force. If we have unlike charges, plus and minus, we have an attractive force. And look at the formula to determine the magnitude of that force. It looks very much like the formula for the gravitational force. It's a constant times the product of the two charges, instead of being the product of the two masses, divided by the square of the distance. So what is this constant here? It's called Coulomb's constant, and it's equal to 9.0 times 10 to the 9, so it's easy to remember, 9 times 10 to the 9, newtons meters squared per Coulomb squared. Very good. So now let's go back to the hydrogen atom with the electron and the proton, and let's try to calculate the electric force of attraction. It's attraction because we have minus and plus. So the attractive electric force between the proton and the electron. Okay, and the data is as follows. The charge of the electron and the proton are both equal to 1.6 times 10 to the minus 19, except that they have opposite signs. So now let's plug this data in the formula and see what happens. And we obtain the following: Coulomb's constant times the product of the two charges divided by the distance squared. And plugging this in the calculator, we obtain approximately 8.2 times 10 to the minus 8 newtons. So now compare this to the gravitational force between the proton and the electron. The gravitational force between the proton and the electron, that was approximately in the order of magnitude of 10 to the minus 47 newtons. So this being in the order of magnitude of 10 to the minus 7 and this 10 to the minus 47, well, 10 to the minus 7 is 40 orders of magnitude above 10 to the minus 47. So clearly the force that predominates the behavior of electrons and protons within an atom is the electric force and not the gravitational force. Moving on to magnetic forces. Fundamentally, they are felt by charges which move inside a magnetic field. Okay, and I represented a purple zone here, which is a magnetic field directed into the page. Okay, so you have to think 3D here. We have a magnetic field of strength B. Okay, and the strength of a magnetic field is measured in Teslas. And we have a symbol here, which is the symbol for a vector which is directed into the page. If I wanted to direct the magnetic field out of the page, I would have drawn a vector like this. Okay, so this whole zone is a magnetic field directed into the page, and I'm going to place a charge in there, a positive charge, okay, of strength of amount q. I have q coulombs of charge, and of course right now if it's at rest it doesn't feel any magnetic force, but if I give it a velocity, for example the downward velocity here, well then it will start feeling a magnetic force. And the goal here is to express the strength of this magnetic force and its direction in terms of these three fundamental variables. And the formula is as follows. The vector for the magnetic force is equal to the amount of charge q times the cross product of the vector, the velocity vector, and the magnetic field vector. So qv cross b. Now first, how do we find the direction of a cross product? Well, we use something called the right-hand rule, where the thumb points in the direction of the first vector, the fingers in the second vector, and the palm will point the direction of the vector we're trying to find, the result of the cross product. So here the first vector is the velocity of the charge, and if it's a positive charge, well, we have a current in this direction. So point your finger, your thumb downwards. Now point your fingers in the direction of the magnetic field, so into the page, and you will find that your palm is pointing towards the right here. So the direction of the magnetic force is towards the right. This is the force vector felt by this moving charge. Okay, so now what about the magnitude of this force? Well, the magnitude of this force is this constant q times the magnitude of this cross product. And what is that? It's v times b, so the magnitude of the velocity vector times the strength of the magnetic field, times the sign of the angle between the velocity and the magnetic field vectors. Okay, let's do a quick application with numbers so that we learn this thing better. Imagine I have a charge Q of 1 nanocoulomb, okay, so a positive charge of 1 nanocoulomb moving in a magnetic field of 1 Tesla with a velocity of 2 meters per second. Okay, so let's apply the formula to find the magnetic force. So I know that it's in the right direction, but what is its magnitude? Well, it's 1 nanocoulomb times 2 meters per second times 1 Tesla times the sine of the angle between this green vector and the B vector, which is into the page. Well, this angle is 90 degrees, so the sine of 90 degrees is just 1. Okay, so let's just multiply by 1 here. And what do I find? 1 times 2 times 10 to the minus 9. So I simply obtain a little force of 2 nanonewtons. Okay, very good. Now, a little trick question. Imagine I had a negative charge of the same magnitude, 1 nanocoulomb, but negative this time. And I make it move in the same direction. Okay, I have a velocity in that direction, which is the same, 2 meters per second. And this time, let's try to find the direction of the magnetic force that's felt by this negative charge. Well, in this case, the current was in the downward direction. But that's when a positive charge is moving downward. But when you have a negative charge moving downward, the current is actually in the opposite direction. Okay, conventional current is the direction of motion of positive charges. So when you have a negative charge moving, the conventional current's direction is in the opposite direction. And you probably learned that when studying electrons traveling around a circuit. Okay, the current is in the direction opposite to the motion of the electrons. So if the current is upward, you point your thumb upward. And if the magnetic field is into the page, so point your fingers into the page, you have a thumb upward, fingers into the page. Well, your palm is pointing towards the left. So in this case, I would have a 2 nanonewton force, but towards the left. Okay, let's enter in the atomic world now and study the strong nuclear force. Fascinating stuff here. It's the attraction between the nucleons inside the nucleus of an atom. And why am I so excited about this stuff? It's crazy. When you look at the distance between the 2 protons inside the nucleus of a helium atom, for example, well, they're separated by a distance of the order of magnitude of 10 to the minus 15 meters. That's a very, very short distance. And we have 2 positive charges here. 2 positive charges that therefore feel a repulsion. They don't like each other. They want to move away from each other with an electric force that's acting on them. And when you do the calculation using Coulomb's law, you find actually that the order of magnitude of this electric force is equal to 100 newtons. Okay, that may not seem that much. It's 10 kilograms, the weight of a 10 kilogram object on the surface of the Earth. But applied to a proton, let me show you how impressive that is. That's a huge force. A proton has a mass of around 10 to the minus 27 kilograms in order of magnitude. If we apply Newton's second law, saying that F is equal to ma and putting the acceleration in terms of the force and the mass, so force divided by mass, and therefore this force of 100 newtons divided by a mass of 10 to the minus 27 kilograms, I obtain an acceleration in the order of magnitude of 10 to the 29 meters per second squared. This is humongous. Knowing that the speed of light is of the order of magnitude of 10 to the 11 meters per second, and that the velocity of an object is its acceleration times time, considering that it starts at rest, it means that the time taken to reach the speed of light, 10 to the 11, when you have an acceleration of, so t equals v over a, when you have an acceleration of 10 to the 29, you obtain 10 to the minus 18 seconds. So if you had a proton freely available in space like this, and you actually could give it a force of 100 newtons, it would reach the speed of light in a billionth of a second. So this is how strong the electric force is between the the protons of a helium atom. But I don't see helium exploding all the time here. The protons are stuck together, so there must be a force that overcomes this already very big electric force. And this force is called the strong nuclear force. Now, something that's rather weird with this strong nuclear force is that it only acts in very short ranges. Okay, it's a short range force. And how short? Well, it only acts when you're at the distance of around 10 to the minus 15 meters, okay? Only a few femtometers. Remember that the size of the atom is somewhere around 10 to the minus 10 meters. So this means that even if I approach a new nucleon, a proton or a neutron, and I dig deep into the atom, and I bring it to a distance of, let's say, 10 femtometers, even that is not enough. Even that, I will just get pushed away. My proton will not fuse with what's existing. I really need to get into that very short range in order for that strong nuclear force to be active. Okay, so it is a short-range force. And now how strong is it? How strong is this nuclear force? Well, we know that it's at least stronger than 100 newtons in this atom, but actually newtons, it doesn't really make sense when you're into the atomic world. We rather talk about binding energy, which is the total energy that you would need to completely pull apart the constituents of a nucleus. So imagine you take this helium nucleus. It's basically the energy that would be required to completely pull apart the four constituents, so the two neutrons and the two protons, and let them be free. And for the helium atom, this binding energy is equal to 28 mega electron volts. Let's see what that means. And for this, I suggest that we try and answer this question. How much work is needed to completely take apart the nuclei that are contained in 1 gram of helium gas? Okay, knowing that this 20 MeV energy refers to the energy needed to take apart the 4 nuclei of one atom only. Okay, so how do I go from 1 atom to 1 gram? Well, first I need to know how much binding energy there is in 1 mole, and for that I multiply by Avogadro's constant, which is 6.02 times 10 to the 23, and I obtain the following figure, about 1.7 times 10 to the 25 MeV, and this time per mole, not per atom. Okay. So now I know that from the table of elements that in 1 mole of helium I have 4 grams. Okay, so since I'm interested in 1 gram, let's divide by 4. And when I divide by 4, I obtain approximately 4.3 times 10 to the 23 MeV, and this time per gram of helium gas. Okay, now I have this MeV thing, and I have electron volts, which correspond to the energy, the work required to move an electron across a potential difference of 1 volt. You'll see that in another video. So let's translate this into joules, and for this I just need to multiply by 1.6 times 10 to the minus 19. That's how much joules, how many joules corresponding to 1 electron volt, and I obtain something like 680,000 million joules. So that's approximately 600 gigajoules we're talking about, knowing that a nuclear power plant produces about 1 gigajoule of energy each second. Well, let's divide this number by 60, and we find approximately 11 minutes of work, of energy that a nuclear power plant produces. So imagine that we could somehow channel all that energy that a nuclear power plant produces in 11 minutes and use it to dislocate 1 gram of helium gas. Well, that's how much energy you would need. This is big. So that's a good representation, I think, of how strong the nuclear force is.